Welcome to the spoken tutorial on improvement of thermal efficiency in modern steam power plant. Learning objectives, basic components and thermodynamic cycle, thermal efficiency, how thermal efficiency can be increased, reheating, example problem solution, conclusion, few observations and a question. We know the ideal thermodynamic cycle for a steam power plant is the Rankine cycle. There are four main components in a steam power plant. This pump, boiler, turbine and condenser. And the Rankine cycle shown in the TS diagram on the right hand side, you can see the different processes which are taking place in those devices. In the pump and turbine, the processes are isentropic, shown by the lines 1, 2 and 3, 4 respectively. And heat addition process which is taking place in the boiler is isobaric in nature, shown by the line 2 to 3. And heat rejection process in the condenser shown by the isobaric line 4-1. Thermal efficiency is defined as 1 minus Q out by Q in. If we consider all the devices of the power plant are steady flow devices, and if we neglect change of kinetic and potential energy with respect to the heat and work interaction with those devices, then we can express this efficiency as 1 minus the ratio of change of enthalpy during heat rejection and heat addition process, simply using steady flow energy equation. And further, if we consider the heat addition and heat rejection processes are reversible in nature, then we can again approximate this is equal to 1 minus T average out by T average in, where T average is defined as ratio of change of enthalpy and change of entropy during the same process. Point to be noted that during heat addition and heat rejection process, change of entropy is same, and that is why the expression of efficiency is a function of, can be expressed as a function of average temperature out and average temperature in. Now efficiency can be increased by lowering the average temperature of heat rejection or by increasing the average temperature of heat addition. Now average temperature of heat rejection can be decreased by decreasing the condenser pressure. That you can see in this diagram. If we reduce the condenser pressure from P4 to P4 prime, average temperature of heat rejection will be decreased. That means efficiency will be increased. But the problem is that if we reduce the condenser pressure, in that case at the final stage of the turbine, dryness fraction decreases with respect to the previous pressure. That means the moisture content will increase at the final stage of the turbine, which ultimately erodes the turbine blades and ultimately reduce the turbine efficiency, which is not desirable. Another problem is that we cannot reduce the condenser pressure at our will. Otherwise, the effective heat transfer with the nearby cooling medium will not be possible in the condenser, because the condenser temperature should be at least 8 to 10 degrees centigrade more than the nearby cooling medium. So lowering of condenser pressure is limited by the saturation pressure corresponding to the temperature of the liquid in the condenser. Now we can increase the average temperature of heat addition either by increasing the boiler pressure. You can see if you increase the boiler pressure from P3 to P3 prime, obviously the average temperature of heat addition will increase. So efficiency will increase. But again the problem is that at the final stage of the turbine, you can see dryness fraction is very less. That means the moisture content is more. So turbine efficiency will decrease, which is not desirable. By superheating to a very high temperature, we can increase the average temperature of heat addition. But again the problem is that we cannot increase this superheating temperature above the material unsafe limit, because from the metallurgical consideration this maximum temperature of superheating is limited. But there is one advantage. You can see not only average temperature of heat addition will increase, that means not only efficiency will increase, but at the same time, by increasing the superheating temperature, the moisture content at the final stage of the turbine is also reduced, so which is desirable thing. But the maximum temperature of superheating is limited by the metallurgical considerations. Now reheating is basically an improvement in the power plant where the expansion of steam in the turbine is done in two stages, and in between the steam is reheated in some intermediate pressure. So by this method, you can see in this diagram, this is basically the ideal reheat Rankine cycle, where you can see the heat addition process, the complete heat addition process is from 2 to 3. This is the heat addition which is taking place in the boiler. After that, the first stage of expansion from 3 to 4. 4 is some intermediate pressure. At this state 4, it goes to the reheater and again the constant pressure heating, and finally last stage of expansion that is taking place in the low pressure turbine. So in this method, we can increase the boiler pressure. You can see we can increase the boiler pressure. That means we can increase the average temperature of heat addition. At the same time, the moisture content at the final stage of the turbine is also very, very less. Now the question is, how many reheating stages? Theoretically, we can see if we increase the number of reheating stages, the average temperature of heat addition will increase. But the actual situation is that if we in a single reheat, thermal efficiency will increase about 4 to 5%. In fact, if we increase the number of reheating stages, in the subsequent stages the efficiency increment will be very, very less and gradually reduced, and that is why more than 2 reheating stages however is not practical, and this gain in efficiency is too small to justify the added cost and complexity. Now if the turbine inlet pressure is not very high, in that case in fact double reheat would result in superheated exhaust, and it would cause the cycle efficiency to decrease, because if the exhaust from the turbine is in the superheated condition, that means average temperature of heat rejection will increase, so efficiency of the cycle will decrease in that case. Generally double reheat stage is used on supercritical pressure boilers. Now one problem will clear the idea of the advantage of reheating and advantage of other processes that we have just described. In this particular problem, we have to find out efficiency and the quality of steam at the exit of the turbine in the following cases. In the case 1, the turbine inlet pressure and temperature is given, condenser pressure is given. Similarly, for other cases, the condenser pressure, turbine inlet temperature and pressures are given, and in the case 5, reheating is done and the reheating pressure is given, condenser pressure and turbine inlet temperature and pressures are given. I will not go into the detail of the problem solution. I will just show you the result, from where what we can conclude is that due to lowering the condenser pressure from 75 kilopascal to 10 kilopascal, efficiency increases 26 to 33.4%, but dryness fraction decreases 88.6 to 81.3%. That means moisture content increases due to lowering of condenser pressure. Now due to superheating, you can see both efficiency is increasing, at the same time dryness fraction is increasing, which are desirable. Due to increasing the boiler pressure from 3 to 15 megapascal, you see that efficiency increased from 37 to 43%, but moisture content is also increased, which is not desirable. Due to incorporation of reheating at 4 megapascal, you can see efficiency is increased about 2%. At the same time, the moisture content is also reduced. That means the dryness fraction is increased, and which is desirable. So the conclusion that we can make is, by incorporating reheating stage or stages, we can take advantage of the increased efficiencies at higher boiler pressures without facing the problem of excessive moisture at the final stages of the turbine. Now from this problem actually we will get an idea about the order of magnitude of different parameters, like boiler pressure generally between 1 megapascal to 30 megapascal, temperature range about 250 to 650 degrees centigrade. Reheat is generally done approximately 1/4 of the boiler pressure. Quality of steam generally more than 80% at the final stage of the turbine exit. Thermal efficiency of the steam power plant are generally less than 50%. Now try to answer this question, that can you think of any other improvement in Rankine cycle to increase the thermal efficiency of steam power plant? Okay, I am giving you hint. Look carefully in the TS diagram that average temperature of heat addition is mainly decreased due to the low temperature of the subcooled region. So try to increase the average temperature in this region. This tutorial is created by the team of the following members from the remote center Techno India Salt Lake, Kolkata, center code 1263. অনির্বাণ বোস টিম লিডার, পার্থসারথী চট্টোপাধ্যায়, মৃণাল ঘোষ, অমিতাভ রয়। থ্যাংক ইউ।